Okay, so I'm recording this lecture now. Welcome back, everyone. We have 1 hour now, and what I wanted to do was to quickly remind you what we've done so far and the essential commands that we have learned. I hope that you guys can see my iPad Blackboard. And so basically what we did was we looked at the idea of a random variable, right? Random variable. And basically what we are talking about here is a function. So capital X will always refer to random variables and small x will refer to an instance of the random variable, right? And so the variable name doesn't matter, okay? So don't be confused. So sometimes if I say y, if I write y and y, then again, I'm talking about a random variable, right? Sometimes later on, you will see Greek letters for random variables, but that doesn't matter what the name is, okay? So what's important is that whenever we define a random variable, we are basically making a statement about what we think is happening out there in nature when we are studying a particular problem. So somebody just asked me in the chat if the capital X random variable refers to the population. The way I would put it is that it refers to the underlying generative process. So when we do an experiment on eye tracking, for example, an eye tracking experiment or an EEG experiment, what we are getting out of that experiment from the subjects is some numbers, right? So the assumption is that there is something producing those numbers. So you can think of it as a population of numbers, but I mean, it's a very abstract concept because there's no such population of numbers. When you do a census, for a country, there is actually a population. There's a finite number of people in Germany, right? That is the population. With reading times, I mean, it's an infinity of possible values. So you can call it a population if you like, but it's actually just the abstract generative process that we are describing. And so, when we have this random variable X, what we are doing is we are defining a function that is mapping every possible outcome into the real number system, which is basically going to be referred to as the support of X. And the support of X will be mapped onto, in the discrete case, it will be mapped onto a 0, 1 value, right? Something between 0 and 1. In the continuous case, the support of X will be mapped onto a density value, which does not have to be between 0 and 1, right? Because remember, this is the discrete case. In the discrete case, we've got a mapping from the support of X to the probability space. In the continuous case, we have a mapping from the support of X to the density. Oops, sorry, I didn't mean to do that. So there's a big difference between the discrete and the continuous case, right? So we looked at all that. And then the other thing we learned was that is everything okay? I'm getting some messages here. Yeah. So what we learned was that there is a D norm function, which gives me the PDF, the probability density function. There's the P norm function, which gives me what? It gives me the, I'm sorry, yes. So it tells me the probability of observing some value like X or something less than that and so on, right? So it gives me this ability to calculate the cumulative distribution. This is the cumulative distribution function, right? And then the Q norm function gives me the inverse of the cumulative distribution, the inverse of the CDF, right? And then finally, we have the R norm function, which generates random data, right? So we saw this. These are the important things I wanted you to learn. And we have, of course, the same family for discrete and continuous. So these are the DP, QR sequence. For every distribution, there will be such a sequence, right? So that's what we learned today. The other thing that we learned was this bivariate and more generally multivariate right? Multivariate distributions. And so, as I explained earlier, if I have two abstract random variables that are somehow correlated or related to each other, I can describe them in terms of a bivariate distribution with some mean and some standard deviation. So I'll just call it mu1, mu2, could be anything. And this distribution could be anything too, like it doesn't have to be a normal, but I always consider the normal case here because that's what we will encounter when we do linear mixed modeling. And so there's something called a variance covariance matrix that determines the standard deviations of the two random variables and the correlation between them. So what does the sigma look like? If you remember, in the bivariate case, the sigma is a symmetric distribution. And what that means, I will just explain. On the diagonals, it's got the variances, and on the off diagonals, it's got the covariance, which is the product of the standard deviations and the correlation. And the reason this is called a symmetric distribution is that the off diagonals, this is an off diagonal element, right? 6x sigma y. Both of these off diagonals, they are identical. And that means if I take this variance covariance matrix and I transpose it, that means if I just take the transpose of this variance covariance matrix, I'm going to get that variance covariance matrix back. That's the meaning of symmetry, right? So there's also a square matrix, as you will notice. It has exactly the same number of rows and columns. So it's an important property of variance covariance matrices that they're symmetric and square. And this property is very important. It has to be respected to actually be a variance covariance matrix. Now, what I want to point out to you guys is that this is a very general framework, this multivariate distribution. If I have three random variables, call them x, y, and z, look at what happens, okay? Now I've got three random variables. Now I'm going to define the normal distribution on 3 dimensions, right? So then I'm going to have mu1, mu2, and mu3, right? Now the fun will begin when we start looking at the sigma here. What will be the dimensions of sigma? Anybody? How many rows and how many columns will sigma have now?
3 by 3.
3 by 3.
Very good. It'll be a 3 by 3 matrix, right? So look at what happens now. If I write this thing out, I need lots of space here. So on the diagonals, what will I have? I'll have the 3 variances: x, sigma x squared, sigma y squared, and sigma z squared, right? And on the off diagonals, and this is where the fun begins, right? On the off diagonals, I'm going to have the pairwise covariances between all the 3 random variables. What that means, this is really significant now. What that means is that I'll have a correlation between x and y, right? That will be in this box. Then I will have a correlation here inside for x and z, right? And then I will have a correlation here, right? This will be between y and z, right? So there will be covariances described in each of these 3 boxes now, right? So it will be sigma x, sigma y. This will be sigma x and z. So sigma x, sigma z. This will be sigma x, sigma y. Now I'm not going to write the covariances here, right? Why not? Because I've already written them here, right? This is going to be symmetric, so it'll be the same thing. So it'll be a 3 by 3 matrix. It'll be a 3 by 3 matrix, and it will contain all the correlations between the random variables, right? And similarly, like I could go on and on. X, Y, Z, W. I could have a 4 random variable thing, and then I would have a 4 by 4 variance covariance matrix, right? So this is a very, very important concept because when we fit linear mixed models, if you remember in the Elmer syntax, right, what's happening underlyingly, right, is that if you have like 3 variables like F1 plus F2 plus F1 interaction F2, right, there's a main effects and interaction type of model, and you set up a random, random structure like F intercept plus F1 plus F2. I hope everybody knows what I'm talking about. Is there anyone who's never seen an Elmer function before? Because if you haven't, then you won't know what I'm saying here. But I will explain all this later if you haven't seen it, okay? Assuming that everybody's seen this before. So if we write something like this, right? This statement here, right? This statement is actually saying that there is a 4x4 variance covariance matrix, right? And this one here will be the intercepts. Oh, sorry, what am I doing here, right? For the subjects, right? There will be a variance associated with the intercept for the subjects. This will be the slope for the standard deviation. Sorry, I should call this F1 squared. This should be sigma F2 squared, and this will be sigma. It's going to get ugly now. F1, F2 squared, and so on, right? So this is what this statement is doing. It's actually describing a 4-dimensional variance covariance matrix. And that's where all the interesting action happens in a linear mixed model, right? So that's why I'm introducing this idea to you. You're going to need this later on. Okay, so that's the story with the variance covariance matrix. And it's actually not very complicated, right? It's pretty straightforward. I will come back to it later when we start discussing this in detail. So now I'm going to go back to my slides. Let me see, maybe I can just stay with my slides on this here. Where is it? Sorry, there's too many of these apps here. Right. Okay, so where we were, we had reached the end of this lecture, except that I just wanted to introduce this idea of maximum likelihood estimation. Right, so where are we? Yeah, here we go, right? So maximum likelihood estimates. Maybe I do need my R here. Okay, so let me share this again, my slides. Right, so what we've got here is what I want to talk to you guys about now is the idea of maximum likelihood estimation. And what is that idea? The idea is the following. Let's think about a simple situation, very, very simple situation. And that is the binomial distribution, right? If you remember in the binomial case, what did we have? We had this function. Just one second here, right? Here is our function. And what this function is saying is that we can compute for, given the probability P, we can calculate the probability of observing K successes out of N trials, right? So what is interesting about this function is that this is actually a probability mass function that's giving us the probability of a particular outcome once we have decided what the probability P is. You have to make a commitment about the probability P to calculate this function, okay? Now, this function can also be seen. There's a very important moment now in this course. This function can be seen as a function of P. Suppose I fix N and K, right? When would I fix N and K? If I've done the experiment, I already know how many successes I have. N is fixed and K is fixed. Both those numbers are constants now. Once you've collected the data, the patient is already dead. There's nothing more you can do, right? You've got fixed numbers now, right? So I've got N and K. The only variable now I have is P, right? So now you can think of this function differently. Earlier, we had thought of this function as a function that gives us the probability of a particular outcome. But now we are going to think of this function, the same function, as a function of P. When we think of the function as a function of the parameter in the PMF or PDF, that function then has a different name. Then it is called a likelihood function. And the reason it's called a likelihood function is that if we plug in different values of P, any number between 0 and 1 into this function, given N and K, okay, we fixed N and K, we will get a different number each time, right? And that different number will be a value that is called a likelihood. Okay, so this is very puzzling, actually, if you think about it. The same function can be seen from two different perspectives. The one hand is a probability mass function, right? If I want to compute the probability and I fix the P, it's a probability mass function. But it's also a likelihood function if I think of N and K as fixed and P as the variable. So what's cool about this, a super interesting fact, is that if I plot all possible values of this likelihood function, right? What would be the possible values? Every value between 0 and 1 for the probability P. What I would get is a smooth, continuous curve, even in the discrete distribution. The likelihood function, which is a function of P, will be a smooth, continuous curve, because it tells you for every possible value of P, what the likelihood will be given the N and K. Right? And a surprising fact will be that the maximum value of that function, the maximum point of that function, will be something called the maximum likelihood estimate. Okay, so let me just try to draw this. I'm going to have to get back to my right. So here's my whiteboard gone. What happened to my whiteboard? Really bad at finding icons. Right? Okay, so so what I'm saying is that I could actually plot the likelihood function in the following way, right? So the likelihood function is this one. I'll call this f of k, right? So this function, sorry, f of theta, no, sorry, f of p is what I want to say. And this function is n choose k, right? These are fixed quantities, fixed. These are actual constants now, right? And I've got p to the power of k and 1 minus p to the power of n minus k. That's the function, okay? So what I'm going to do is on the x-axis, I'm going to have p, which will vary from 0 to 1. And on the y-axis, I will have the likelihood, the result of this computation for every possible value of p, right? So likelihood, right? And so if I plot this likelihood for, let's say I have k equal to 50 and n equal to 100, right? Suppose that's what I have as my constants here, these fixed values here, right? So in that case, what will happen is that this curve will look like this. It will have a maximum value at 0.5. Why is that? It's because k, I've set k equal to 50 and n equal to 100. This is my data. This is my actual data from an experiment, right? And so what's interesting about this is that if I have k successes out of n, the maximum point in this likelihood function curve will be this point k over n. Whatever k is. If k is 0.3, then if k is 30, let's say 30, then the maximum point will be 30 over 100 and so on, right? And so that's why this quantity k over n is called the maximum likelihood estimate, MLE, right? This maximum likelihood estimate tells you the maximum point on this curve for all possible values of the parameter. Are we good? Is this clear? Right, so how would this work in practice? How would I actually compute this computationally, like using R or whatever, right? Let's try this. Okay, so let's play with this idea a little bit now, right? You should be able to see my R screen, my RStudio screen now. Let me know if that's not the case. Okay.
Yeah.
Yeah, very good. Yeah. So let's see. Let's play with this a bit. Okay. So likelihood functions. So let's take the simple case of the binomial, right? I've got, let's say, 50 successes out of 100. And I can think of some probability like 0.5, right? So this quantity now, right? 50 and 100 are my fixed quantities. That's the data I've observed. And what I'm doing is I'm computing the likelihood for this particular probability, okay? When I do that, I get some value here. This is now seen as a function of the probability P. This is actually a likelihood for me, right? So I could actually, what I could do is I could actually compute every possible value or lots of values between 0 and 1, right? This is all the, a range of possible values of P, right? So I could compute the likelihood for all of them. Could compute the likelihood of all of them. And look at what happens now. I've got a bunch of values, right? For all possible values of P. I mean, exaggerating a little bit because of course I'm discretizing the P, right? P is a continuous value between 0 and 1, but I can't show you an infinity of values. So that's why I'm taking a smaller number. And so, but what you should notice is that for the smallest value of P, that is 0, I get a likelihood of 0, right? That's the y-axis. And for the largest value, I get, again, 0. So I could actually plot these values now, right? So let me call these likelihoods, right? All different possible values. And I could plot them against this sequence of, values that I use to compute the likelihood. This is my x-axis now, right? So I'll call this x, right? Or let's call this the different P's, right? It's easier to understand maybe. And then I could plot, hopefully this will work. Just doing this on the fly, it usually doesn't work if you do it on the fly. What is it? Type, I think, type. When I plot this function is actually, this is a likelihood function. On the y-axis, I have the likelihoods. On the x-axis, I have the different possible values. Now, if I had had, let's say, 30 successes, okay? 30 successes. Let's take a look at what the shape of this distribution is now. See that? It's shifted to 30%. If I had 90 successes out of 100, this is my data. It's fixed. It's a fixed quantity. What's happening is that the likelihood function is shifting to the right with a maximum point at 90, right? So that is why when we compute k over n, right? So whatever k is and whatever n is, this gives us the maximum likelihood estimate. It gives us the point in the curve that has the maximum point. This point, it tells us what this x value, this probability value is in the likelihood function. Whenever when we compute the k over n. And you must have done this whenever you calculate the number of proportion of successes. The reason why this is such an important quantity is because it's telling you the maximum point in the likelihood function. And that's why it's called a maximum likelihood estimate. So this is the discrete case. The same thing happens in the continuous case. Okay, so the continuous case, let's go back to the end of the slides. So let's look here, right? So what we are talking about here is there's some parameter in your particular probability mass function or density function, call it theta. There is some data that you have, right? And you can plot that this function as a function of the theta values. That's what we are doing here. That's what I just showed you, right? And so in the normal case, you will have something similar, right? Suppose So what happens in the normal case is that you can have different possible values for the mean. These are different possible values for the mean. And on the y-axis, what you're getting is the likelihoods of each of these possible values, right? So what's important to notice here is that in the continuous case, right, instead of D binom, suppose I was working with D norm, right? Sorry, once I've fixed, I have to rewrite all this here. I'm talking about the normal distribution now. So suppose I'm choosing some mean value and some standard deviation value. So let's fix the standard deviation to 1 because we want to simplify our problem. We want to think of this function, the D norm function, which was the probability density function. We're going to think of it as the likelihood function. Okay, how do we do that? Let's say we got some data like, let's say 1.5 is the data that we have observed. This could be an ERP experiment, right? That's a plausible value you could explore, you could observe. So for different values of this mean, I've just observed this one data point, by the way. This is just one data point from the experiment, okay? And I have some fixed standard deviation, I'm assuming, just for simplicity. I can now compute this function for different values of the mean, right? I could put in a 1 here. I could put in a 2 here. I could put in a 3 here. So this function is a function of this mean now, right? And what you'll find is that for each of these values for the mean, you'll get a different likelihood. Let me start printing it out and show you, okay? For 1, I'll get this number, 0.35. If I say 2, I'll get a smaller number. Well, it doesn't change actually. What happened here? I guess it doesn't really change that much. If I change it to 20, I'm getting a really small number. Do you see that? 1.9 times 10 to the power of minus 75. You see that? So the likelihood will change depending on what the mean is here, right? So what I can do is I can take a sequence of values, let's say from -2 to 2 by 0.001 or something like this, right? So I could plot the likelihood for every possible value in that list of the sequence of values, right? And so I could save this as a likelihood function. Remember that I have literally just one data point, 1.5, okay? This is my data, this is a constant. I'm just looking at the function as a function of this mean. So if I plot this, I can do the same kind of plot that I showed you earlier. I'll likelihood on the y-axis. On the x-axis, I'm going to have the same sequence. I'll just copy it out. I'm going to plot the likelihood as a function of the different possible values of mu, or the mean that I put in. I put this here. If I plot this function, lo and behold, what do I see? Where is the maximum value in this function? Can you guess?
1.5.
It's 1.5. Exactly, right? Because I have only one data point. That data point is the mean of that data point. And the mean from the data is always going to give you that maximum point in the likelihood function. That's the importance of the mean calculation. When you do the k over n in the discrete case, you're calculating the mean. That's also a maximum likelihood estimate. Right? So it's possible to prove mathematically that the sample mean, and the k over n in the discrete case, these things are going to be the maximum likelihood estimate. This is just an analytical mathematical proof. Super easy to do. If you've seen it, you'll be surprised at how easy it is to prove this mathematically, right? But we can also see this graphically, that this is the maximum likelihood estimate. The mean is the maximum likelihood estimate for the normal and also in the discrete case, right? So this is a very important concept of a maximum likelihood estimate. The reason it's so important for us in Bayes, right, is that what's going to happen later on is when we fit models, is that when we figure out the estimate of the posterior distribution of each parameter, that posterior distribution is going to be a compromise between the mean of the prior distribution and the mean of the maximum likelihood estimate. It's going to be a compromise between those two things, right? And so this is why the concept of a maximum likelihood estimate is very important to have in your mind. Now, I also want to point out that we could have had more than one data point, right? So then what would happen is, suppose I had 2 data points, okay? So I have a day, my data consists not of one data point usually, right? I usually have 2 data points, let's say, or more than 2 data points, right? Let's say 1.5 and 2 is my data, right? Suppose that this is my data. So imagine now, right, that each of these 2 data points is independent of each other. So I could have gotten them from different subjects, for example, right? Instead of 1 data point, I have 2 independent data points, right? So I'm assuming that they are independent. How could I figure out the joint likelihood of these 2 data points? I know how to figure out the likelihood of each of these data points. I just showed you how to do that. So let me just do it for you one more time, right? So the likelihood for 1.5 would be this thing, right? So I won't write this likelihood in terms of a sequence of values, but I'll just say that for some mean, right? So for some mean, I won't specify that yet, right? For some mean, I can compute the likelihood for 1.5. And for some, for the other data point, 2, all I have to do is change the data to 2. Then I could compute the likelihood function for that data point. But what I'm asking you is, how do I figure out the joint likelihood of these 2 data points? Right? I could compute this likelihood somehow, right? By putting in some value for the mean. I could figure out this likelihood for this value, for this data point. So let's say, suppose I want to use mean, well, let's just say mean 0, right? For these 2 values, for this value of the mean, I can compute the likelihood of each of these 2 numbers, right? So likelihood 1 is some number 0.12, and for likelihood 2, I've got some number here, 0.05, right? So my question for you is, how do I compute the joint likelihood of these 2 data points, these 2 independent data points? Any suggestions? Just try to guess.
Multiplication for each point.
Very good, right? There are 2 independent data points, right? So if I want the joint likelihood, I'm just going to multiply the 2 likelihoods. That gives me the joint likelihood. Now, there's a simpler way to do this. Multiplication is always problematic because you have these very small numbers, and trying to multiply lots and lots of small numbers can land you in problems computationally. So one thing you can do is that you can, instead of looking at the likelihood, you can look at the log likelihood. If you take the log of the likelihood, what do I have to change here now? This is going to be the log likelihood now.
It's addition.
Very good, right? So this becomes, this now is much simpler for us computationally. I'm going to be taking the log of the likelihoods, and then instead of multiplying, I just add them up. This is a spectacular achievement, because what will happen to us in real life is that we will have a bunch of data points, a long list of data points. Let me just do it. Let's look at some real data for a second, okay? This is my bcogSci package. I can just extract some data, my favorite data set, which you will see again and again. Right, so I'm just loading some data here, right? So what will happen in this data set, I'm just not used to this keyboard. Right, so what happens in this data set is that I've got some subjects, right? I've got 42 subjects, I've got 16 items, I've got 2 conditions in this experiment, and I'm recording some reading times. These reading times are the data that I'm getting, just like these 2 data points here, right? Like, where are they? These 2 data points here, right? So I'm getting all this data from subjects, right? And underlyingly, I'm going to make some assumptions about which random variable is assumed to have generated this data. That's where we are going with all this, okay? But what's interesting is that I can now compute the likelihood, the joint likelihood of all these data. Of course, there are some complications because I have repeated measurements from each subject. So this data point 320 and 424 are not independent, right? They're correlated, but we will deal with that problem. What I'm showing you is that when I have independent data, I can compute the joint log likelihood of all the data by just summing up the log likelihoods of each of the data points. This will become super important when we are defining a Bayesian model, because we will be adding the log likelihoods later. Okay? This will be part of the modeling that we'll do later on. Are we good? Is everything okay so far? Okay. So this is what I was actually writing here. So what I've done here is that you can write out what I just did formally. Like if you have n data points, x1 to xn, which are a function of some parameter theta, you can compute this function, which we are going to call the joint likelihood of all the data points. Did somebody have a question? I heard some clicks here. Okay, so this is what I've been showing you so far, how to compute the joint log likelihood, right? Given multiple data points. All right. So it's all very simple, it's no problem, right? So, and I already showed you that the mean in the normal distribution and also in the binomial that we saw, the mean and the variance will give you the maximum likelihood estimates. So these are the points on the x-axis, for the parameter for the mean and for the variance that gives you the maximum point in that curve without having to plot the curve or do anything like that, right? So this is the importance of the maximum likelihood estimate, and we will look at this later on. We will use this idea later on. So let's do a few exercises just to like get a feel for everything we've learned so far. Okay. So the first thing I want you guys to think about is, like, suppose I had suppose I had a random variable, right? I'll call this x. Can you see this? Can you guys see what I'm writing?
Yes. Yep.
Okay. Yeah. So suppose I have a random variable x that's coming from a normal distribution with mu equal to, I don't know, 500 and standard deviation equal to 100, right? Suppose I ask you the question, what's the probability of observing a value between, let's say, 300 and 600? Okay, so what's the probability of observing this range of values? How would you do that? Any suggestions? I want you to work out the answer. Give me some suggestions.
Use the Mbr Norm function.
Very good. P norm.
Calculate the P norm for 600 minus P norm for 300.
Very good. Yeah, exactly. This is the calculation I'll have to do. I'll have to specify the mean and the standard deviation. Standard deviation, right? So what was the mean? 500. Standard deviation was 100, right? And here also I have to give the same information, right? So I'll just copy it over. This tells me the difference, the probability within that range. That's 0.81, right? Suppose I wanted to know the probability of observing observing some value greater than 600. X is greater than 600. Suppose I want this. How do I do that? I still have to use the P norm function.
You can use the lower tail argument, maybe.
Mm-hmm. See, when I write this function here, so this one here, this is telling me the probability of 600 or something less than that, right? So what that is actually saying is that the default value of lower tail is, I think, true, right? That's the default value. Let's check that. By the way, get used to like looking up the help when you don't know something. Yeah. So question mark P norm will tell me what the default value for lower tail is. See that? Lower tail equal to true. That's the default value for P norm. So therefore, what this is doing is, it's telling you the area under the curve to the left of the number you've specified. So if I want to know the area under the curve to the right of the number I've specified, all I have to do is set this to false. Right? If I set this to false, it tells me the area to the right of 600.15. Okay. Okay, so that's P norm. That pretty much covers all the possibilities, right? Now, what about if I want to know, so what is the quantile Q, right? Such that probability of X being less than Q, sorry, less than Q is 0.4. How do I find this answer out? What function do I need for that?
You know.
Exactly. Q norm is the inverse of the CDF. So it takes as input a probability for a given mean and a given standard deviation. In this case, 500 and 100, right? And so if I hit enter now, it tells me the number. Tells me the number such that the probability to the left of it is 0.4. Are we good? That's what this Q norm function does. Now, the last thing I want to show you guys is how would I compute some random data? If I want to generate some random data, how would I do that? I would use the R norm function. R norm function. Let's say I produce 1,000 data points with a mean 500, standard deviation 100. I could call this Y, right? I could plot this data. This is random data now, right? It's just randomly generated data centered around 500 with a standard deviation of 100, right? And I could repeatedly do this. I get slightly different data each time. See that? Different data each time. This is how I will be simulating this data. Now, once I've collected some data, can I compute the joint likelihood of this data? Absolutely. D norm, Y, mean 500, standard deviation 100, log, true, right? I get the log likelihood of all the data, right? And if I sum it up, what do I get? Get the joint likelihood, log likelihood of all the data. Super cool, right?
Sorry, so how would we interpret this now? Like
How do we interpret? How do we interpret what exactly?
The minus 6,000. What does it tell us?
Yes,
What
yes.
does
How do
the
you?
value tell us here?
Okay. Yes, this is what I want you guys to play with now. Okay. Change the mean to 100. Okay. Now, I've generated this data Y with mean 500. Are you with me? Very important point. I generate this data with mean 500. This means that the maximum likelihood estimate of Y is what? 500, right? So now I'm going to change the mean in this likelihood calculation and compare the joint likelihood with this number here, okay? Take a look at what happens now. Is the likelihood smaller now or larger? For mean 100,
Smaller.
where does the confusion come from? Yes, somebody said
Because it's the
larger.
log likelihood.
It's a more negative number.
Exactly. So this is very confusing, okay? Because when you see 6,025, this seems smaller than 14,000, but don't forget the negative sign in front of it, right? Minus 14,000 is much smaller than 6,000. So what's happening is that 500, this parameter value 500 is much more likely than the parameter value 100. In fact, 500 will be the most likely value that you will get, right? Will give you the highest likelihood for this data, the highest joint likelihood. You can check that. Try this, okay? Try 500.1. Let's see what happens now. That shouldn't change much, but let's say 505, okay? Close to 500. 6,024, 6,025, right? So what's happening here is that, do you understand why the likelihood is actually higher for 505 compared to 500? That's technically not true. That's actually not true, but it's just as a function of the random data that I happen to generate. Okay, if I had produced another data set, I would have gotten a different likelihood. And the reason is that, what is the mean? What is the mean of y here? The mean of y is 504, right? So with 505, I actually got closer to the maximum likelihood estimate of these data. Are you with me? Right? So if in this function, if I put in, sorry, if I put in, what has happened here? Sorry, I wanted to type mean of y. If I put in the mean of y, the observed data y, as the possible value one, this will be the maximum value in the data, in this likelihood calculation. This number will be the largest possible number in the joint likelihood. Any other number that I choose here is going to be slightly smaller. The likelihood will be smaller, right? So 504 should give me a, yeah, you see that 0.414 becomes 0.431. So the likelihood has gone down slightly. If I use 506, likelihood will go down slightly, right? It's 504 compared to 414 here, the decimal places. Of course, the likelihood is changing very little because we are very close to the sample mean. But the important point here is that the sample mean, the mean of y, is the maximum likelihood estimate, right? By definition, this output will be the maximum value that's possible, given this data. The data are constant, remember that, right? So this likelihood, joint likelihood, is now going to be the maximum value for the mean of y. For every other value that you put in here, you will get a lower likelihood, okay? So that's the important thing that you should know, the relevance of the D norm function in this case here. And you'll notice, you know, like, let's go back to that actual data set that I had set up. Where was it? I've got it loaded right now, right? So if I were to fit this, right, this is what we normally do when we are doing data analysis. We fit a model like Elmer, RT. I'm fitting it incorrectly right now. It doesn't matter, right? So I've got condition. And let's say I put in 1 subj and df, what was it? df gg05 rc, I think it was, right? Yeah, so if I run this function, right, and I plot the output of this model, right, what happens is, what this model at least used to print out, it doesn't do that anymore. Oh yeah, so let me, sorry, what I want to demonstrate is the following, sorry, just one second. When I do a hypothesis test, you know, with the linear mixed model, take a look at this. I could fit a null model, right, without the predictor present, right? And now I can do an Anova analysis of variance. I'm sure you guys have done this before, right? So I can compare these two models with the likelihood ratio test, right? When I do this comparison, look here, see that log likelihood over there? The model is producing the log likelihood of the full model and of the null model, right? And the analysis of variance is actually comparing these two log likelihoods and trying to decide which of these two models better represents the data, right? And the way the calculation is done, this chi-squared value is -2 times the difference of these two log likelihoods, right? And it's this minus 2 times the difference that tells us whether there's a significant difference between M and M null. It's all based on this log likelihood. And that's where all this is coming from. This is that maximum likelihood estimation that we just did, okay? So this is where I'm going with all this, that we will be looking, this will become a crucial quantity for us, the log likelihood of a model, right? For model comparison and also for other things. Okay, so basically this was the main story so far. The very last point I want to cover is what happened here? Yeah, I want to talk about bivariate distributions, just to give you a feeling for how I would do, how we could generate random data. The same things, you know, that you learned in the univariate case, they are now going to map on to the multivariate case. We can just expand this to a multivariate situation. So let's do that, okay? First, I'm going to load the library mass. This library actually has this very interesting function called Mbr. So Mbr norm. So remember the R norm function? We just looked at it. We are now going to use the multivariate R norm function to generate random data that is correlated, okay? So how do I do that? Well, let me look up the help, because I always forget how to do this, right? So the Mbr norm function asks you to define how many data points you want to generate. So let's say I want to generate 100 data points, and it asks you to define the mu and the big sigma. The big sigma, remember, is the variance covariance matrix. So the mu is easy to define. If I want to generate a bivariate distribution, let's say that the mu is 0, right? For both the random variables. I need to figure out how to define this variance covariance matrix, this VCOV matrix, right? How do I work it out? I have to do some work there now. So let's do this work, right? VCOV matrix, right? I'm going to define a matrix with values, let's say 1 along the diagonals and a correlation of 0.6 in the off diagonal. So how do I do this? I always forget these commands. Like, I don't know, like it's just never sticks in my head. So how is a matrix defined? The matrix is defined by the number of rows and number of columns, right? So number of columns will be, ncol will be 2 because it's a bivariate distribution. And so this should give me, sorry, this is not correct. I've written it in the wrong place, sorry. I meant to write it here, ncol equal to 2. This should give me a variance covariance matrix that has the right shape that I want. Let's see, let's take a look. Right, see that? This is a symmetric matrix. Let me check that, okay? Let's check the symmetry of this matrix. Take the VCOV matrix. I'm gonna transform this matrix, right? Make the rows columns and make the columns rows. That's what the T does. It's a transform function, right? And I get exactly the same matrix back. See that? It's pretty cool. It's exactly the same matrix. So it's a symmetric matrix, right? So I've defined my variance covariance matrix on the diagonals of this matrix. Oh, sorry, let me go back. The diagonal of this matrix contains the variances, and the off diagonal contains the covariances, right? So it's going to be also the correlation. Why? Because the variances are 1 and 1. So I'm multiplying the standard deviation, which is 1 and 1, with 0.6. So I get 0.6, right? If I'd set a different standard deviation, let me do that, right? Let's say instead of 1, if I had 100 and 200, let's say, as my standard deviations, then what would the variance covariance matrix look like? It would look very different, right? It says, this is the variance, by the way. These are variances I'm giving it, 100 and 200. And the off diagonals will no longer be 0.6. What would the off diagonals be? Tell me what to write here. What do I have to write here now? To define the covariance, covariance, how do I do that?
Two variances and correlation.
Say again, I didn't get that once again.
Sorry, the two variances, the multiplication of the two variances and the correlation coefficient.
Yes, except that it's not the multiplication of the of the variances, but of the standard deviations. So the square
Okay.
root, yes, square root of 100 times the square root of 200, right? So this gives me the covariance. Very good. That's exactly what I wanted. I have to repeat that here, right? And now I get the correct variance covariance matrix, right? I've got the covariances here, and I've got the variances here. So I'm all set, right? So now, once I've defined this V-curve matrix, I plug it into this Mbr norm function. And this Mbr norm function is now going to generate 100 correlated data points, which will be provided in a matrix form. Why? Why is it in a matrix form? It has 100 rows and 2 columns. That's because each data point is a pair of data points. It's a pair of data points. And that's why I'm getting a pair out like this, right? 100 by 2 matrix. So I'm going to call this U, okay? And now I can actually plot this. Let's take a look at what this thing looks like. I'll take the first column and plot it against the, or rather plot the second column against the first column. And when I do that, look at this. This is correlated data that I just produced. You see that? Pretty cool. If I set this correlation to minus 0.6 here, right? If I set it to minus 0.6, look at what happens to the distribution. The shape of the distribution has changed. You see that? What would happen if I set it to 0? What would this look like now? Tell me.
Just a shapeless cloud.
It will be a blob, completely symmetric blob. Well, it doesn't look completely symmetric. You know, if you squint, it looks like there might be some correlation or something. This is what happens in psycholinguistics journals also, right? You got like 5 data points and it looks like there's a correlation. So let's try this, okay? This is fun to see how noise can look like a signal, right? Suppose I have 10 data points. We have top journal articles with 10 data points, you know, plotting correlations. So let's see what happens now. Oh no, this I didn't mean to change this to 10. So I've got this covariance here. No correlation, okay, between anything. You see that the variance covariance matrix reflects the fact that there is no correlation, right? I can generate 10 data points and I could plot them. And well, this doesn't look like there's something going on. Well, let's try it again. I will eventually get some data that looks like it's correlated. Maybe 10 is too little. Here, this one's nice. Right? This looks like there might be something going on. Do you see that? This gets published in top journals, this kind of stuff. And I'm not joking. I'm not exaggerating at all. This is very normal to see, oh, wow, like there's something going on here. It's pure noise. Correlation is 0, right? So this is a very instructive exercise to play with data to get a feeling for what is noise and what is signal. Once you know the ground truth, you can develop a bit more of a skeptical outlook, you know, when you see these kinds of plots, right? All right, but the application that we will have, you know, for this kind of thing is not to study the problems in journal articles, but actually to generate fake data. We will generate simulated data to understand the properties of the models that we are fitting. That's what the purpose is for us, okay? Okay, so I think we are now ready to do some interesting work next week. I want you guys to do the 4 exercises that I've specified on the homepage for chapter 1. These are very easy exercises, just asking you to use P norm, Q norm, and maybe the bivariate case I think I have, and try to play around with that and do those exercises. I will give you the solutions, but I mean, it's really easy. Given what I've shown you so far, it should not be too challenging. However, if you get stuck and if you have some problems, you can always post those questions on Slack, or during the exercise period, you can ask Anna and Paula. I will try to be there as well, so we'll see what happens. One other thing you should do during the remainder, after lunch, you get 1.5 hours, take a look at the lecture notes and try to, quickly look at the points that I've laid out. They are in more detail over there. You don't have to read everything in the lecture notes, not right now anyway. Do that later on, right? But you can review the points that I have explained today in the lecture notes there, and you'll get a better understanding of what's going on. Are we okay? Are there any questions right now? I still have a few minutes. We can talk if there are any burning questions. Oh yeah, there's some questions here on the chat that I can answer. Let me just do that. Yeah, so one very interesting question is, what's going on with that singularity warning, what means the singular Elmer here, right? So let me show you what the question is about. So I think that what must have happened is when I fit that linear mixed model, right? So where is the model summary? Right, in this model, sometimes you will get a singularity warning, right, when you fit such a model. So let me try fitting it and see what happens. Let me just do this quickly and see if I can generate a singularity. Yes, I remember I can generate a singularity here. So this is a very important point actually that I should have mentioned. I forgot to do that. So let's say I fit a model like this, subj plus this is called the maximal model in psycholinguistics, and it would be something like item got varying intercepts and slopes for everything that I could possibly have here. And so it's GG05, what is it, 05 RC, right? I fit this model, I get this boundary singular fit. C is singular. What's going on here? This actually this warning relates to the variance covariance matrix. So there's a problem in the variance covariance matrix. And the problem is the following. Let's look at the output. What's happening in this output is that this output here, the random effects, is actually showing you the shape of the variance covariance matrix. Here you have the variance of the first random variable for subjects, the intercept. Here's the variance of the second random variable, the slope for the subjects. And here you're seeing the correlation between those two. That was in the off diagonal. If you remember in the variance covariance matrix, I put in the correlation into the covariance, right? And the correlation is here -1. So what happens is that if the correlation is +1 or -1, the matrix becomes non-invertible, right? So in statistics, whenever you have a variance covariance matrix, right, like this one here, this one that I defined earlier, whenever you have this variance covariance matrix, so I don't want this to be 0, let's call this a 1, right? Let's set up the matrix to have correlation 1, okay? Or let's say -1, it doesn't matter, whichever one you decide, right? So when you have a correlation of -1, this variance covariance matrix is going to be singular. What that means is that if I try to invert this matrix, it should not invert. It should not be invertible, right? The reason it's not invertible is that the inverse of a 2x2 matrix is the product of these two things minus the product of these two things. And that will be the value 0. And whenever the value is 0, that matrix is not invertible. And if a matrix is not invertible, you cannot compute the parameter estimates in the model. Right? So of course, the Elmer model actually does produce parameter estimates, right? All these parameter estimates have been computed, but this matrix is not an appropriate matrix for a data generative process. It's describing an impossible data generative process because this matrix is not invertible, and the inversion of the matrix is necessary for computing the standard error of these fixed effects. So this is a serious problem. This is actually a very serious problem. It represents, the singularity warning represents an inappropriate model for the data. Of course, the estimates are still being printed out, and that's why psycholinguists will still produce in their papers the estimates of these models, even with singular fits. People do this all the time, right? But technically, this is not an appropriate model anymore. And what you should be doing in this particular case is that you should not even attempt to try to estimate the correlation. And as you guys know, in Elmer, the way we do that is by switching off the correlation completely. So we are now assuming no correlation at all. And if I fit this model, I still get a singularity warning. So what is that about, right? So let's look at the output. So what happens in this case is that the two of the variance components here, they're coming out as singular. So if any of the variances is zero, is not coming out as singular, it's coming out as zero. When any of the variances is zero, as they are here, then the matrix will again be singular. It will not be invertible because the products of the diagonals with the off diagonal subtracted and with the off diagonal subtracted from it will also be zero, right? Because there's a zero term there. So whenever the variances are zero or the correlation is +1 or -1, you're going to end up with a non-invertible matrix, with a singular matrix. It's the same thing. There's a small bug in Elmer that produces these correlations. It shouldn't be turning up, but I will explain all this later on. It's not important right now. What's important is to understand what this singularity warning is. All this is telling you is that the variance covariance matrix for the random effect is not invertible. Therefore, the model is not appropriate. Okay, we will fix all this later on when we are working with actual data. Okay, did I answer the question? Is it okay? All right. Okay. Any other questions before we stop for now? Okay, if not, I'm going to stop recording. And